So in this video, we're going to be talking about roots and radicals, which is just another name for a root. So if you're asked to find the indicated nth roots of a, it's just a funny way of asking you to find roots other than just square roots. So the n tells you what kind of a root you're taking. So in this case, it's asking for the third root of negative 216. Usually we are uncomfortable with negatives underneath a radical sign or root sign because we think of them as imaginary numbers. Now, if it's a square root or any other even root, it would be imaginary. You're not allowed to have a negative under a square root. You can't get that. But a negative number underneath a cube root is okay because a negative times a negative times a negative does give a negative output. So this one does have a solution. It's negative 6 because negative 6 times itself 3 times does give negative 216. So cube roots can be negative or they can be positive. Fourth roots, because it's an even number, must be positive. When you multiply something by itself an even number of times, will always give you a positive. So if you had a negative under here, you would have to say that it's not real. So just note, if you had this as the question, the answer is going to be not real. It's imaginary, but we're not going to get into imaginary solutions, so you don't need to worry about them right now. And the n value inside here is called the index. So as you hear me use that vocabulary word, index, the plural is indices. That's what I'm talking about. Because it sometimes gets asked about for even roots, just know that the principal root is the positive one. So you don't always have to put plus or minus in front of an even root. Sometimes I get asked this, right? So the square root of 36, if it just says this on a piece of paper, they are asking you for the positive square root of 36. Although, you know that negative 6 times negative 6 also gives you 36. If they wanted the negative answer, they would have to ask for the negative root, which would look like this, right? They would have to put the negative in front so that you would know they're looking for the negative answer. And if they want both, then they need to show both in front of the radical sign. Plus or minus 36 underneath the root would be plus or minus 6 as the answer. When you are solving an equation for x, for example, x squared equals 36, you're looking for all the possible values for x that work, positive and negative alike. And so you would need to show the plus or minus in front of your radical in order to get both solutions. So x would equal plus or minus 6. So that's why your algebra teacher is always harping on show the plus or minus in front of your square root symbol to make sure you're getting both answers. Some properties of radicals. So if you have the same index, right, these two radicals have the same index, you can multiply. So if you had the square root of 3 multiplied by the square root of 7, you can combine them and make it the square root of 21. If you had the square root of 5 times the square root of 5, here's the helpful one, right? We don't know those square roots individually. They're not rational numbers. But if you combine it to be root 25, well, then you can simplify that because you know the square root of 25 is 5. So it's a useful property for simplifying, as is the division property or the quotient property of radicals. Again, if you have the same index, so like the third root of 81 divided by the third root of 3. Neither one of these has a cube root that's a perfect whole number, but when I consolidate this to one radical, I have 81 thirds as the fraction. I simplify that to 27, and now I do know the cube root of 27 is 3, so that can be a useful property as well. We don't need to do all these examples, but we could look at just part C here. Because they're both square roots, I can combine, make it 48 over 3. That does simplify to the square root of 16, and that's something I know. So you can see how these properties are nice at times. Writing something in simplest radical form or surd form. This is when it's not a perfect square or perfect cube, but you are supposed to simplify, like if you're doing the Pythagorean theorem and this is what you get as the answer. You should factor it into two factors. Sorry, my pen is being funny. Factor it into two factors of 80. Let me just delete these. Where one of the factors is a perfect square. Now, 80 itself is not a perfect square, but I can think of at least one number that goes into it that is a perfect square. I'm trying to think of the biggest factor of 80 that is a perfect square, and I know that that's 16. 16 times 5 is 80, and root 16 is 4, the whole rational number 4. Radical 5 is just radical 5. It doesn't get simplified at all. And so this is the simplest radical form of root 80. That's considered a better answer than root 80. If you have cube roots, you're going to want to be separating it into two factors where one is a perfect cube. So you should memorize some of your perfect cubes, as in the first 7 perhaps, so that you know what to look for when you're simplifying these. I'll just list them out so you can list them out in your notes, though of course you can come up with these anytime. You need to know 1 cubed is 1, and 2 cubed is 8, and 3 cubed is 27. You're going to have to get used to noticing these. A 64, a 125, a 216 that we saw earlier in this lesson, and a 343. And up through 10 would be nice to memorize, but these are the ones that come up the most. So 54 we can break into 27 and 2, noting that the cube root of 27 is 3, the whole rational number 3, and cube root 2 just sticks there as part of the answer in simplest radical form. We don't need to practice all of these. Another requirement for simplest radical form, so if you come up with an answer of 1 over the square root of 2, is that you can't leave a denominator irrational, and square root of 2 is an irrational number. So to deal with these, we multiply the numerator and denominator of this fraction by the same thing, which we're allowed to do because that's basically just multiplying by 1. And the numerator will become uglier, right? 1 times root 2 is root 2, but the denominator becomes nice and rational because root 2 times root 2 is root 4. And root 4 simplifies to 2. So the denominator has become this lovely rational 2, and who cares about the numerator? It's ugly, but that's allowed. Let's just do this example B here. The 4 is not what's causing us the problem, it's the square root, that is, the root 10. So it's okay to just multiply by root 10 over root 10, since that's what's causing all the trouble. The numerator will become the square root of 70 if I'm following my property that says I'm allowed to multiply with the same index. And the denominator will become 4 times square root 10 times square root 10, which is square root 100, which is just 10. And so this ends up being the square root of 70 over 40. And it would be good to think about simplifying that root 70, but I can't think of any perfect squares that go into that. Combining radical expressions by adding and subtracting. Note you can only do this if they're exactly the same radical, as in they have the same index and the same number under the radical sign, which is called the radicand. Okay, so like I can subtract and add if I have a square root 3 plus, let's say, 5 square root 3. This is kind of just like combining like terms. I can combine those and get 6 square root 3, right? Because there's 1 of these and 5 of those, and therefore you can add them together. It may be necessary to simplify if you have an expression like the one here before adding and subtracting, because right now the root 12, the root 75, and the root 3, they sure don't look identical. But if I simplify root 12, I can get 2 root 3, right? That's the simplest radical form of root 12. If I simplify the root 75, I can get 5 root 3. And this last term is already 1 root 3. I'll just put the 1 in front so you can see it. And then, of course, I do have all the same radicals, so I can combine 2 plus 5 minus 1 and get 6 root 3 as the simplified version of this addition and subtraction problem. But if your roots are different, so root 2 plus root 3, that's it, right? You cannot simplify that any further because they're not the same radical. Products of binomials when you have radicals in them. It's going to be a binomial times a binomial, so expansion or FOIL, if that's what you like to call it. So we'll do first, outer, inner, last. In the interest of time, I'm going to skip this example, but it is going to be useful to see it done when it's a conjugate pair. So a conjugate pair is specifically binomials that are almost identical, but one's plus and one's minus as the sign in the middle. And so when I FOIL these, or distribute these, 5 times 5 is 25. The 5 times positive root 7 will end up canceling out with the 5 times negative root 7. The final term becomes rational because a root 7 times a root 7 is going to be minus root 49, which is just 7. Sorry about that long tail. Okay, the middle terms will cancel out. That's the whole idea of a conjugate pair, that the middle terms cancel out. And then 25 minus 7 gives us 18. So conjugate pairs, when they FOIL out and expand fully, become nice rational numbers. And so that's going to be useful when we have to do something like this, rationalizing a denominator that has a binomial. You'll want to multiply by the conjugate. So root 5 plus root 2. Root 5 plus root 2. Whatever you do to the bottom, do the identical thing to the top, because that's like multiplying by 1. The numerator will become a little bit uglier. We have to distribute here. So 3 root 2 times root 5 is 3 root 10. 3 root 2 times root 2 is 3 times the square root of 4, which is 3 times 2, which is 6. So the numerator has become this. The denominator is going to be a FOIL. So root 5 times root 5 is 5. The middle two terms will cancel out because they're conjugate pairs. And the last two terms are root 2 times root 2, so minus 2, which simplifies. We've done all the hard stuff now. It's just the simplifying to this, right? 5 minus 2 is just 3 on the denominator. And then when you have a fraction over a whole number, you can think about it as two separate fractions over that whole number and see if either piece or both pieces can be simplified, which they indeed can. 3 root 10 over 3 is just root 10, and 6 over 3 is just 2. And so that's what this ends up being after it's rationalized. And that is all.